A really cool result in quantum mechanics is Heisenberg's uncertainty principle. And this is a principle that tells us certain pairs of quantities cannot be simultaneously determined with absolute precision. So let me explain what that means. We're going to talk about a couple of examples of measurable quantities that are linked by an uncertainty relation. So these are going to be, the first one we're going to talk about is delta x, delta p. So that is an uncertainty between, and I'll write an x here, I'll explain why in a moment. This is uncertainty between position and momentum. And the other pair we're going to look at is delta E, delta T. And that will be the subject for the next video because these deltas have a slightly different meaning. So let's focus on this one first. Now, in this uncertainty relationship, we basically have the position of a particle in a particular axis. Now, I'll stress that if we imagine 3D space, so I'll draw some axes over here, and say this was x, y, and z. Oops, I didn't mean to cross that out. This uncertainty relation is basically telling us, let me just remove that, is basically telling us that the delta x, the uncertainty in x, so you've used uncertainty a lot in first year physics, hopefully so far, so you know what this means. It has some formal meanings, which we're not going to discuss, but essentially treat this as just delta the quantity, the uncertainty of that. So uncertainty in position and the uncertainty in momentum in the same direction. So this is an important thing to note here. I'll finish writing this. It's greater than or equal to h bar on 2, where h bar is the reduced Planck's constant. That's just Planck's constant divided by 2 pi. So, back to this explanation here. Basically what this is saying is, if you know the position of a particle very precisely on, say, the x-axis, so we knew it was right here, we knew exactly, very, very precisely where it was on x, that would mean that delta x is small. We have a small uncertainty in its position. What this inequality tells us is that the product of the uncertainty in the position and the uncertainty in the momentum in that direction, so how basically what its momentum is along this axis, is fundamentally confined to be bigger than h bar on 2. So what that means is if the uncertainty in x, for example, is very, very small, in order for this inequality to hold, the uncertainty in the momentum in the x direction would need to be very large. And for that reason, the more precisely we know, say, the position, the less precisely we know the momentum. So let me show you an example of this. Let's say, for instance, that we knew the position of a particle to within 1 nanometer. So delta x is 1 nanometer, or we'll say 1.0 times 10 to the minus 9 meters. Then how precisely could we know our uncertainty in our how precisely could we know our momentum value? In other words, what is delta p? So delta x, delta p is greater than or equal to h bar on 2. So rearranging this, we have the uncertainty in momentum is greater than or equal to h bar divided by 2 delta x. And if we then calculate that, so we know that h bar is, so I'll kind of rewrite this, that's just the regular Planck's constant over 2 pi, so it's 4 pi delta x. So substituting all of these values, given our delta x value up here, into a calculator, you will end up with an uncertainty momentum of 5.27 times 10 to the minus 26 kilogram meters per second. And I'll add an extra significant figure up here so that we're consistent with having 3. The important factor here is that, we can see that the smaller this delta x is, the larger this uncertainty in momentum is going to get. And the other thing to be aware of is that you need to be using SI units, or at least a consistent set of units, when you're substituting into this relationship. And h, Planck's constant, has units as well. So you should be sticking to, as long as you're using our regular value of h, 6.626 times 10 to the minus 34 joules seconds. You need to be using SI units for your uncertainty values, delta x and delta p, and the other uncertainty relations that we're going to talk about. So we've seen that there is this relationship. The next thing to talk about is why this is. Now, we're not going to be able to perform the full formal derivation in this course. However, there are a few things that you'll find interesting that might help you understand a bit about what's going on here. Now, the first thing I'm going to talk about is that this uncertainty relationship is not due to our lack of ability to measure. Essentially, regardless of how good our instrumentations are, we can't measure beyond this limit, this fundamental uncertainty limit. And further, there is another kind of concept that is often conflated with the Heisenberg uncertainty principle, which is the fact that making a measurement actually disrupts the system. And I'll explain why this principle can sort of be derived from a completely different idea in a sec, but there's this idea that, well, let's say we want to measure the position of our particle on this axis. To figure out where it is, maybe we have to shine some photons on it, and so they would impact, and then we figure out where it is. We've made an observation, but by shining a photon on it, we've also disturbed it in some way. The photon has given it momentum, and now its momentum is different. So we've disturbed momentum by measuring position. However, although this is a true phenomenon, this problem with measurement, you can see why Heisenberg's uncertainty principle is true just using the wave nature of matter. So, you will recall from our discussion of matter waves that the wavelength of a particle is given by Planck's constant divided by its momentum. So, in other words, it's the momentum and the wavelength are linked in some way. We've talked about that link for a while. Now, to see why this is relevant, let's consider this. So I'm going to draw two waves here. So one of them, it doesn't look that consistent, but let's imagine this is a nice consistent sine wave, and the other one here looks something like this. All right. Now, we can see here that one of these waves, the top wave, because it is consistent and sort of stretches off, it has a very well-defined wavelength. We could easily sort of go in and measure that, figure out what the wavelength is. Now, that wave corresponds to a particle, that matter wave corresponds to a particle with well-defined momentum. It has a well-defined wavelength, so by the de Broglie relation, its momentum is also well-defined. Because, of course, we could rearrange this, and we'd end up with momentum is equal to Planck's constant divided by wavelength. However, this wave does not have a well-defined position. There's no real one place you could point and say that's where the particle is. It appears to be sort of spread over space. Now, this second wave does have what appears to be a very well-defined position. So you can see that it's kind of all our wave is kind of spiking here, and then it's there's no wave anywhere else. However, this very well localized wave doesn't have an obvious wavelength. It doesn't really make sense to refer to a wavelength when what you have isn't a nice long continuous wave, but in fact just a little pulse. So this is with no real. This is not a formal proof. This is really a very qualitative look at what's going on here. But you can basically see that having a wave with well-defined momentum, so this would be delta p is small, the momentum is well-defined because the wavelength is well-defined. This down here would be delta x is small. It's a clear position. It's got a clear position. It's just a pulse at one point. However, it doesn't have a well-defined wavelength, so the uncertainty in momentum is large. You can see that when describing particles as waves, the position and momentum cannot be perfectly defined together just because of that wave nature. So this is really interesting, and if you go on to study more quantum physics, you will get a better idea of the real formalism underpinning where this relationship comes from.